Hi, my name is Tyler.
And I'm Patrick, and this is our design project PowerPoint. So you got to forgive us here since we used Google Slides instead of PowerPoint, and we weren't able to narrate over a presentation. So we're going to make this YouTube video here and just play it alongside your actual going through of the PowerPoint. So we'll tell you when it's time to switch slides, and switch slides.
The decision matrix. The way we did this is we took the different designs that each of us came up with. We then came up with several different constraints and then graded them accordingly. Afterwards, we were able to figure out which one was going to be the most optimal design, and then we changed it a tiny bit to make everything work the way we wanted it to. Next slide.
So here are our design alternatives. As you can see, the designs that we had or created were all really based upon centripetal motion. We didn't really consider the possibility of switching from centripetal motion to linear motion, and we pretty much had an idea from the get-go of what we wanted, and we went with it. So, next slide.
The initial model, we decided to keep it fairly simple with a simple belt system. We initially thought that we would need to increase the torque and lower the speed because we thought the motor would be faster. So we ran from pulley to another pulley, gearing up the ratio, or gearing down the ratio, so that way we would lose speed but increase the torque that we would need. Later we found out that the motor was extremely slow and had plenty of torque, so we did the opposite and geared it up so that way it would be much faster but lower the torque, but it was still able to run everything that we needed. This design was really simple and only needed a handful of parts.
Next slide. So over here is just pretty much a labeling of all the important parts on that initial design. Next slide.
Here is our first initial design of our impeller. As you can see, it was 6 inches in diameter and pretty simple. We found out that this was way too big. It would take way too much torque to move this, and the motor couldn't handle it, and it was just going to be unrealistic to use this type of model.
Next slide. So here's our second impeller design. So we decided to shrink it down to a 4-inch diameter and add this conical design to the base of the impeller. This was so that we could hopefully increase the amount of water flowing towards the edges of the impeller. After our initial testing, we thought this model was also too big. Although in actuality, we just hadn't primed the design. So that kind of guaranteed failure there. But such is life. Next slide. This is our third design of the impeller. And as you can see, we made it even smaller, only 2.5 inches in diameter. We kept that conical design, but this time pitched the impeller blades too. So pitching these impeller blades was a bit of a hassle and required some math there, which was fairly simple. Just a point on the top of the impeller, a point on the rim of the impeller, and then 2 points that highlighted the route, I would say, of the impeller tip or impeller blade top. So after some quick math, or some long math rather, I was able to finally figure that out. And after some testing, we were able to get some water to be pumped out of this design. However, the major flaw though was with the impeller casing rather than the impeller. Next slide.
Here you can see our impeller casing. The green arrow going around is the direction of the motor, the direction of the impeller as it spins. The red lines is the centripetal motion that any motion would have off of those impellers. The problem that we ran into was we put the output hole, which is on the side of it, on the bottom, and it was no longer parallel to our centripetal tangent lines coming off of the motion. This was our design flaw, and we knew afterwards, after a little bit of figuring out, that the output direction needed to be on the top and not the bottom. Also, the problem with our casing was in the print, and that it was not as waterproof as it needed to be to properly get the water sealed in there and create the vacuum that it really needed to move the water.
Next slide. So here's just an overview of the final design. Pretty nice, huh? Next slide.
Here you can see all the different things labeled. We started off with the gears at the bottom coming straight off the motor, going from the biggest gear to the smallest gear. That smallest gear is then matched up with the biggest timing belt, and then goes all the way across to our axle with the smallest timing belt. That then goes into the impeller casing, which moves the impeller.
So the basic operation of our pump, next slide. So the basic operation of this pump was pretty straightforward. As the impeller spins, it creates a centrifugal force on the water within the casing. This water is then pushed towards the wall of the casing. At the center of the impeller, a negative pressure is created. And in order to balance out this negative pressure, water is pulled into the pump. The water is then pushed out through the exit pipe. So the gear ratio that we used in order to help create enough speed for the impeller to move was 17.222. Next slide.
Here you can see our casing, our impeller, and our lid. When we were printing it, it was important to consider how everything would fit together. So we knew we needed to print it in 3 different parts, the insides and the outsides, but to get the inside in the inside, we needed to make it in 2 different parts, the casing and the lid, which we then sealed up with glue. Next slide.
So here are several pictures. On the left here is a picture of the final design, and on the right is a picture of that 3D printed part. Next slide.
Here you can see again some more of the parts. You see a little bit closer, you can see our gears and our timing belt, how it works. Our idler spot that kept some tension on the belt, which was just the right amount, where it wasn't causing too much friction on the motor, but it was just enough to keep the gears and the pulley from slipping. On the right, you see the casing and the lid put together, or not put together, but separated, and those were just glued together and made a pretty good seal.
So here's a video of our pump working. So we'll give you about 40 seconds to watch it. Starting now. Pretty neat, huh? Next slide.
Here you can see our trial performance. In the first trial, we ran it in a clockwise motion, and it had an average current of 506 milliamp hours. The minimum that it ran was 383, and the max was 627. It was fairly consistent as it went through because we weren't moving, the volume of water that we were moving wasn't constantly changing. It was fairly consistent as all the pipes were filled and it was constantly full. The trial 2 performance was a little different. We ran it in a counterclockwise direction, and it had a lower average current of 178 milliamp hours. The minimum was 35 and the max 279. As you can see, it moved a little bit more in the counterclockwise direction. This direction was not as efficient as it should have been.
Next slide. So here's just a quick budget. Our final design budget was $1,208. Our total budget, including all the parts that we didn't use and the failed 3D printed parts, was $1,672. Next slide.
Recommendation for improvement. So several things that we could have changed to make this work a little bit better. If we had sealed the case properly, making it 100% waterproof, that would have made a big difference in helping with the vacuum and the movement of water. There was a slight gap in the middle of the casing that allowed water to flow into it, and some water was leaking out that, as well as the back where the axle came into the casing. Also, if we had corrected the casing output direction, we feel that would have made the largest difference, as it would have actually been doing what it was supposed to be doing and gotten the water out in the direction it was supposed to, instead of going against into a perpendicular angle and go parallel like it was supposed to.
So thanks for watching our presentation. I hope you enjoyed it, and I enjoyed this project a lot.
We both did. Thank you very much.
Goodbye.